Hey guys, Spencer here. Today we're going to be going over how to create a neural network from scratch. There are going to be two steps in this process. One is going to be the theory base. I'm going to be going over the feed forward and the back propagation. And the second part is just bringing everything together in terms of a code structure. I'm going to be creating a basic neural network from scratch, utilizing the theory from previously. Neural networks are used almost everywhere in today's society, whether it's right in front of you in terms of image recognition or autonomous vehicles, or it could be slowly behind the scenes, such as predictions on human behavior, social networks, social dilemma, if you saw that movie. Everything utilizes a neural network because it's such a great tool to solve a non-linear problem. If you like what you see so far, please make sure you hit that like button and subscribe. It really helps out with the growth of this channel. I do some really cool stuff related to data science and also the financial industry. So if you're interested in that, please make sure you check out my other videos as well, and I'll see you over there. In fact, if you haven't seen my latest video on GAN, I highly recommend that you check that one out. It utilizes some pretty sophisticated architecture related to neural networks to generate something really, really cool. So I hope that you do check that out. And so throughout this entire video, I'm going to give you the rundown on what you pretty much really need to know, what you can extract from this, and how you can apply this into everyday life, so to say, to improve your own lifestyle or maybe even create your own product. So let's take this step by step and let's begin with the theory. Alright, so let's begin with the basics of the neural network. So the motivation behind developing a neural network was to help solve nonlinear problems. Many of the linear problems that we have, like a y is equal to mx plus b problem, already has a model associated with that, like a linear regression. You got the polynomial regression and variances of the logistic regression. Now, what happens if we're trying to solve a nonlinear problem such as image recognition, natural language processing, autonomous vehicle recognition, or self-driving cars? That is where the neural networks come into play. And the neural networks, they have a very interesting history behind them, because at one point there was no research being done on neural networks because there was just a lack of theory, and also the lack of computers that would help substantiate all of these really, really cool findings. But now we're here, and neural networks are largely driving the 21st century theories and applications. It's really fascinating. So I'm going to be going over the steps of how to essentially recreate the neural network. The first step is to define your model architecture, and this is where pretty much all of your money is going to go to if you are starting from like a research and development point of view, just optimizing on these input layers, hidden layers, number of nodes within your hidden layers. That takes up a lot of money to essentially just find your corresponding weights. Second step, you got to initialize your parameters. Like, what are your beginning weights going to be, how many nodes you got, etc. Third step, you'll be creating a for loop. So this will be essentially epoching through your architecture. An epoch is essentially the feed forward and the back propagation. It's taking all these steps all at once, just going through the for loop. That's essentially what it is. I'll be going a little bit more into detail on what that entails, but this is the first part of the epoch. You essentially just pass in your inputs and you go through the entire network. Just go through the entire network, and you have an output, and you essentially use this output and you compute a loss. You compare this loss, and you just input this loss back, and you do back propagation, where you just keep on passing back your results to update your weights. And you do that with an optimization function. It could be a gradient descent, or it can be a variation of gradient descent, such as stochastic gradient descent, or ADAM, which is a updated version, so to say, on the optimization function. So this is essentially the basics of the neural network framework. So let's dig into the feed forward part of the neural network. So I have a very simple model. I have my input layer, I have one hidden layer, and an output layer. Whether or not it's going to be a regression or a classification problem, it really just depends on what type of activation function can be going to use, but in this case we can keep it even more simple. So we have 3 layers. We got input layer, hidden layer, output layer. Notice that I have the bias. The bias is always associated with each of the hidden layers. There's always one bias associated with each layer, including the output layer. The bias is essentially just the intercept term for that given layer. So the first part is that we're going to have weights associated with each connection between one node of the input layer and each of the nodes in the next layer, and it keeps on going on and on and on. So you have all of these connections going on. So as you can see, it's always going to be passed through. There's always a connection between one node and another node. And note that this is a very basic neural network. There are some neural networks that don't have connections to some other nodes, but that's getting off topic here. But each of these connections has a weight assigned to it. Now, the second part, we're going to have the input over here, and we're going to be doing some, essentially just some dot products or some matrix multiplications on where you are essentially multiplying, or you're doing the matrix multiplication of your input and your weights, and you generate some number, some value of where you're essentially just, you multiply your input weight at your ith connection, your I plus 1, I plus 2, I plus 3, and then and I plus 4, and then you keep on, you just sum them all up and you have one single number. You pass this single number into an activation function. In this case, the activation function I'm using is like a simple sigmoid. It just squeezes your numbers down to like a certain range. In this case, it will be 0 to 1. And you just keep on doing this throughout the entire neural network. That's really all you're doing. So like once you have one number here, they keep on doing the same thing what they did here. They do matrix multiplication on this weight, that weight, and you have this input, that output, and then you get one more number over here. And you keep on doing that until you get to your output layer, where you can also just plug in that number into your activation function here. Note that each layer could actually have its own activation function, and that's just where it gets a little bit more hairy, so to say, because everything, once your neural network gets really large, it's really hard to determine what type of output or what effect it would have on your overall neural network. So I just kept everything simple, and I just put the activation function as a sigmoid for each of the layers. Okay, so now that we traverse through the entire neural network, at the very end, we want to take our steps backwards, and we're gonna have a recurrent process on where essentially we want to re-update the weights within our entire infrastructure, our neural network infrastructure. And we do this so that we can minimize our overall error, and we just have a better prediction as a result. So starting at the very end of our neural network, once we've done our feed forward process, we want to first make sure that we calculate our gradient. The gradient is a derivative of our activation functions, and so since our activation functions for this particular example was the sigmoid, this is the derivative of the sigmoid. I just conveniently put the derivative on there. And so once we have that, we can now utilize our given predicted output from our feed forward network from over here, the output value. We calculate the error, so we get our predicted output and our true output. We subtract the two, and that is our error right there, and we want to minimize that via the optimization function of gradient descent. So utilizing the recurrent approach, we are now going to be calculating the error, and we can denote it as d. So we're going to multiply the error and multiply that by the gradient of x, where x is the predicted output. So we are passing in the value of our output into the gradient function, and that is going to be our d value there. And then the next step after that is we need to calculate the error output layer, and we do that by multiplying the d value over here, and we multiply that by the weights of our output layer, so the weights over here. That is going to be the output layer over here. And then what we do there is that we get our error output layer, and we multiply that by the gradient of our given output layer, where x sub 1 is the sum product of our inputs and our weights that are coming into this black circle, black node over here. And this black node has the given gradient over here, where we are going to be plugging in the sum product of all of our values, which should only just be one value. We'll be passing that into the gradient function over here, where we are going to have a DH value there. After that, we are now going to be recalculating or re-updating the weights of our output layer. So these lines, 3 lines over here, they're going to be re-updated. We're going to be adding just plus minus the input value, which are the inputs that are going to be coming here, the activation values from these green circles over here, or green nodes. We're going to be multiplying our matrix multiply that with the DH value we have up here, and we are going to be multiplying that value by the learning rate. So essentially what a learning rate is the size of our steps that we are going to be taking in order to approach a global maximum or a global minimum. And that's just like the size on how we want to inch forward. So the smaller your learning rate is, the longer your overall algorithm will run, and it will have quote unquote higher precision. And so there's always this really neat optimization game on where we need to find our global maximum, global minimum, but we want to take the least amount of time in order to find where those values exist. And that's where the beauty of where most of these optimization functions come into play. And to my knowledge, Atom is the best to do that. It's very like industry widely accepted practice from there. But moving on, the last portion is to calculate the bias, and all you do here is that you just sum up all of your values within your DH over here, and then you just multiply that by the learning rate, and that is your bias. Same exact thing is going to be done with all of your hidden layers. You calculate your error of your hidden layer, where your D value, we're still going to be using the same D value of error times your gradient of your X. We'll be multiplying this by the weights of our output layer again, and then we are still going to be iterating through. We just get the error of the hidden layers. And notice that we are using the weights of our output layer. Since we are working backwards, that is where we are going to be utilizing those weights instead of using the weights of of these over here. So we keep on going backwards so that we can update our weights via there. I just want to point that out. But the next step is to calculate again the DH1. I denoted this as the error hidden layer. You multiply this by the gradient of your X underscore 1. This gradient could be the same, it could be different from your other gradient over here, but for this purpose of this example, the sigmoid is going to be universally used throughout this entire infrastructure. But notice that this gradient could be different from this gradient if we use different activation functions. X sub 1, that is the same thing. This is going to be our X, it's going to be our output of this particular activation layer. Of this layer. So we're just like inputting these values. So each of these hidden layers have a different activation value output, and we're just going to be using those outputs to just plug it back in to just recalculate all of our given parameters to update our weights. And then we just add this to our weights of a hidden layer, the input, multiply that by your DH1, multiply that by your learning rate, and same thing for your bias. Notice that the plus equals this value input dot product DH1 multiplied by learning rate. It could be a negative value as well, so it can fluctuate up and down. So yeah, that is essentially what the entire neural network is. Let's jump to the code so that we can just hammer this understanding down in Python. So let's go to it. Okay, so over here, I just created a real quick notebook on how to create your own neural network from scratch. Note that there are standardized practices, packages to utilize when you're actually utilizing huge neural networks, because there's so many great built-in functions that you could use. Keras is one, TensorFlow if you want to go even more ground in the weeds, so to say. But this, for the purpose of learning and just understanding how to utilize neural networks and how they actually work, we are going to be doing somewhat of a ground zero approach on how to just like learn how these neural networks work. So over here, I imported 3 different, your standard data science type packages. You got NumPy, and you got datasets and pandas. So I'm going to be loading a credit card CSV file. It's essentially like this really neat dataset on Kaggle, where they just give you a bunch of variables and you want to predict the class, whether or not there is potential fraud. So 0 being there is no fraud, and 1 meaning there is fraud. And so for the purpose of this demonstration, I'm going to be cutting down this data set. I'm just going to be taking the first 1,000 rows over here, and I am going to be doing some additional cleaning where I'm just going to get this very last class over here and just convert that to its own set, and where I'm going to have it over here. So I'm going to be getting the X and Y values. Everything is going to be in a NumPy array, where I have my X's over here, my Y's are over here, and just printed the X's and Y's. And it looks like all of my values are going to be 0. So I could probably just randomize that, but whatever. But this is just like for just demonstration purposes. So we should expect all of our values to be 0. So type X, we got a NumPy array. And so this is where our meat and potatoes are going to be at. So we have a sigmoid function. I just defined that. This could be our activation function, and our gradient is going to be the derivatives of the sigmoid, which is just x times 1 minus x. Let's run this. And then this is going to be our initialization parameters. We can have 50 epochs. Learning rate, we could probably put this to 0.01. Our input neurons is going to be the shape. So this is the number of columns within our x value. And then we have the number of hidden neurons within our hidden layer. And I gotta have 5. And our output layer is going to be 1. So it really depends on how many nodes you would want at the very end. If you have a multiple classification type algorithm, you are probably going to want more than one of those outputs. But if you're just doing a regression, like if you want like a number between 0 and like 1,000,000, for instance, then you're going to only want 1 output neuron. But if you're going to be using like a binary classification, for instance, then you can utilize 1 neuron utilizing a softmax function, or you can just stick with 2 neurons with a sigmoid function. But I digress. There's just really neat ways on how you would want to create your overall architecture to approach a particular problem, whether it be classification or regression. Okay, so let's run this, and then we have the initialization of our weights. We have the weights that are hidden, we got our bias, we got the weights of the outer layer, and we got the bias of the outer layer. And I just randomized that, got it from the uniform distribution. And then this is where our entire neural network lives. So we have our hidden layers, 1 hidden layer, 1 input layer, and we have 1 output layer. And notice that like in more complex type of an architecture, just to be like potentially tens, maybe even hundreds of hidden layers that have different processes and activation functions within them. And it just gets way more complicated, but the end result is usually the same in terms of how everything works. So once you understand this, you can definitely apply this to more fancy type architectures. So first part here, we could be doing the forward propagation or the feed forward, which this is where we could be going through the entire architecture. So we are going to have some matrix multiplication happen. We can add our bias in there. We'll be passing in the input into our sigmoid, which is going to be our activation value. And then we're going to be passing in the hidden layer activations, do the dot product between the input values that are coming in and the output weights. And then essentially you just keep on doing this until you don't have any more, no more like hidden layers or just layers in general to do. And then your output, you always put that into your given your output layer. So this is going to be your output, and this is where our error is going to be calculated. So our y value, as earlier we had our y values over here, we are going to calculate a loss value. And we're just going to be subtracting the two. So our predicted value from here, we subtract the two, y minus your output, that is your error. And then this is where we backpropagate. We have the given output. We pass this into our gradient, or not a gradient, our activation. Oh yeah, that is our gradient, sorry. We'll be passing in our output into our gradient. We get the gradient of our output layer. And then we're going to be doing the exact same thing for the gradient of our hidden layer, where our hidden layer activations is the output of our given a given feed forward. So the output of each of the hidden layers has an associated value that's going to be passed in when you're doing the backpropagation. So just do take that in mind. The D output, we have the error, and you multiply that by your gradient output layer, and then you have your error of your hidden layer. You multiply that dot product by the D output, which is right here. You got your error of your output layer, and you do that with your weights of your outer. And then essentially you just do the exact same thing for your hidden layer and all the other hidden layers that you may have in the future or within your architecture. You got your bias as well. Make sure you sum that up, just using some fancy NumPy sums. And that is essentially what the neural network is going to do. So these are all of our predictions, and notice that it should all be 0 technically of our output. Yeah, so that is this is gonna be like the final predictions. So I have a print output over here, and these values are pretty close to 0, which should be expected because the only thing that's coming in are zeros. So yeah, we have the length of our outputs, and we just print this out, and all of our values are 0. Yeah. Granted that the example that I was using was not totally randomized. I should definitely have more ones in here. But bottom line is, the more you train a neural network, the more likely you are going to have quote unquote more accurate results. Partly because on like whatever data that you're feeding into the neural network itself is going to be training itself to understand that data based on those weights. And the more large your data set is, the longer it will take your actual algorithm to run. And you could be waiting for like hundreds of hours, maybe even years, if you are working with a really ugly type data set and the data is just so massive. And there are several ways to try and improve your overall model. The best way is to, well, quote unquote best way is to use an architecture. Just like re-update your architecture to suit your particular problem or need. And in general, in the data science industry, that's very expensive to do and takes some really sharp thinking to figure out, what is the best approach to make your overall model better. But there are other ways, like as in like cleaning your data set and just making your data set more like streamlined. You gotta normalize everything, take out your outliers, convert everything to a number, so on and so forth. But the entire industry, the neural network, is incredibly useful, and in the future I only predict that we are going to be using this stuff more and more often until it just becomes commonplace, and we can have some really cool gadgets in the future that are going to be utilizing this type of technology. I'm happy to see that you made it to the end of this video. If you liked it, make sure you like this video, subscribe, turn those notifications on, maybe even send this video to people who may not really totally understand what neural networks are and what they potentially could do. If you have any questions about neural networks or anything in general, please let me know down in the comments down below. And I hope to see you in the next one. Thank you guys so much for watching.